in this theorem, it's telling us that we can also manipulate a power series through differentiation or through integration. And in particular, if I have a power series representation, Cn x minus a to the n, with a radius of convergence r, then the function f, defined by that power series, is differentiable, and hence continuous, on the interval a minus r to a plus r. In other words, its interval of convergence. The interior of its interval of convergence. And its derivative, f prime, is equal to the term-by-term derivative of the power series. And since each term of the power series is just a simple power function, this makes it particularly simple to take the derivative, because we know that power functions are very easy to differentiate. We just apply the power rule. And that's all we're doing here. We're applying the power rule to each term of the power series, right? So we take the power down and subtract 1 from the power for each term. That's it. And similarly, if we want to integrate the power series, we can just do term-by-term integration of the power series by adding 1 to the power and dividing by the new power. So it's just doing the power rule for antiderivatives. And that's it. And one other conclusion that we can draw is that in each case, the radius of convergence is the same, although it may or may not include the endpoints of the interval of convergence after we manipulate it through differentiation or through integration. So that's always something that we should check if we need to know exactly which values will be included in the interval of convergence. So let's demonstrate with some examples. For instance, here, if I wanted to take the derivative of, if you guys remember our Bessel function from a previous section, we want to take its derivative, which in this case we can just take the derivative of the x to the n term, and all the other stuff in this is just a constant. So keep in mind here, all it is just taking the derivative of x to the 2n by using the power rule. So in this case here, you can imagine we're just basically leaving everything untouched except for x to the 2n. We're going to apply the power rule. So it'll be, take the power down, so it'll be 2n times x to the 2n minus 1. Everything else is just a constant multiple, so we don't need to worry about changing anything else. One thing we should keep in mind, though, is because here the series starts with n equals 0. Therefore, the first term of the series is a constant term. And now that after I differentiate it, that constant term is turned to 0. Now the series should start with n equals 1 as the first term. Okay, and we can verify that just quickly here if I were to write out, say, the first few terms of this series, and then compare it with the first few terms of the derivative. Okay, so when n equals 0, the first term of this series will just be 1 over here 0 in the denominator would also give me 1. So the first term of the series is 1. It's a constant. And then the next term of the series will be, when n equals 1, we get negative x squared over 4 times 1 factorial, which is 1. So minus x squared over 4. And then the next term we can imagine here, we can just do n equals 2. Would give me positive 1 there, x to the 4th. And then here when we put n equals 2 down here, we'll have 2 to the power of 2 times 2, so that's 2 to the power of 4, which is 16. And then n 2 factorial is 2 squared is 4. Okay. Anyway, so just looking at those three terms, we can easily take their derivative and compare that with the three terms that we get here. Notice that here the derivative of the first term is 0, so we don't need to include that. And that's exactly why here we're starting at n equals 1 instead. So now the first term of this series will be the derivative of negative x squared over 4. So we see when n equals 1, let's see what we get. I get negative 1, and then 2 times x to the power of 2 minus 1. So just 2x upstairs. Notice that's exactly the derivative of x squared. And then the denominator, I get 4 again, just like we have here. So we can see that that's the derivative of that term there. And same here, if I take the next term here, n equals 2, we'll have positive 1, 4, x to the 4 minus 1 is x to the 3, so we have 4x cubed. And that's exactly the derivative of x to the 4th. And then notice the denominator didn't change. It's still the same as it was before. Okay, so there we see that it's just taking the derivative of these terms here. If I want to express the function 1 over 1 minus x with the square on the outside there as a power series, we can think of it as the derivative of the function 1 over 1 minus x. We know that the power series of 1 over 1 minus x we wrote earlier as the series x to the n. And this is the one that we were using to manipulate the power series, 1 plus x squared, x cubed, and so on. So if I take the derivative of 1 over 1 minus x squared, or sorry, 1 over 1 minus x, what do I get? Well, we can think of this as the derivative of 1 minus x to the negative 1 power, which will be negative 1 minus x to the negative 2 power, and then times the derivative of 1 minus x, which is negative 1. So that changes it to a positive 1 minus x to the negative 2 power, which is really just what we have, 1 over 1 minus x, quantity squared. So we see that if we take the derivative of this function here, we're going to get exactly the function 1 over 1 minus x, quantity squared. So let's just take the term-by-term derivative of this power series x to the n. Which of course is just doing the power rule to the x to the n term, so we know that's going to be nx to the n minus 1. Now it's starting with n equals 1 to infinity. So you can double check to see that that gives you the same terms that we would get if we were to just take the derivative of each term of the series when it's written out term by term. So it'd be 1 plus 2x plus 3x squared, 4x cubed, and so on. So here we have a power series representation of 1 over 1 minus x, quantity squared. In this example, we want to find a power series representation of the function ln of 1 plus x. Now in this case, what we might want to consider is manipulating the function 1 over 1 plus x through integration. And the reason is because we know that the integral of 1 over 1 plus x is exactly the function we're trying to express here. And we know that the function 1 over 1 plus x can be written as 1 over 1 minus negative x. And we know that this is the power series negative x to the n. Or in this case, if I split it up, negative 1 to the n, x to the n, we can see it's an alternating series. So therefore ln of 1 plus x will be the term-by-term integration of this series. Okay. And again, to integrate, we'll ignore the negative 1 to the n and just integrate the x to the n factor. And the reason again is because negative 1 to the n is like a constant multiple, and x to the n is our power function that we're integrating. Okay. Now I'll put a c in front because that's our constant of integration here. And then we'll just apply the antiderivative power rule to x to the n. So negative 1 to the n doesn't change, and then we get x to the n plus 1 over n plus 1. So here we have the power series of ln of 1 plus x, but now we can also try and think about what this value of c would be. So let's just pull this aside over here for a moment. If I were to substitute x equals 0 into both sides of this equation, well, then I would just be replacing x equals 0 here, which is of course just 0. Right, so that's just 0. So we have ln of 1 equals c plus 0. And ln of 1, of course, is 0. So that gives me c is equal to 0. So in fact, we don't need this c here. We can remove that, and that would be our power series here would be the series n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. Let's look at the terms of the series here. Notice it's an alternating series. And starting with n equals 0, we have x to the 1 over 1. So it's just x for the first term. And then it's alternating, so when n equals 1, it'll be minus x squared over 2. Plus x cubed over 3. Minus x to the 4th over 4. And so on. One thing I might do to rewrite this is to reindex the series here to make it look a little better. For instance, I can index it to start with n equals 1 instead of n equals 0. As we see, that kind of matches how this first term looks. It's just x to the n over n. Then I have to make sure it starts with an odd or an positive term there. So I'll do negative 1 to the n minus 1, and then write x to the n over n. And that generates the same terms that we see here. Now the question is, what's the radius of convergence? And we really just have to think about this one step here, where we were putting in negative x for x. And so again here, we know it's going to be convergent when the absolute value of negative x is less than 1, because that's what we were substituting in for x into that power series, x to the n. And of course that's the same as saying that the absolute value of positive x is less than 1. So here we get our radius of convergence as 1.